wonderful students. We're going to go on to 603. Maybe we'll even do one for 604 before we even meet. We'll see. But this is the help video for 603. Let's see how people are doing. Pretty good. Okay. This is always what we want. We always kind of want this trend this way. And I'm always thankful for your hard work. If ever we see it in the reverse, I definitely think hard about why, what's happening, right? For me, myself, how can I support you? How did I let you down? So thank you for always trying your best. It gives me very important information, and then I've got to figure out what to do about it. So view copy. Okay. We can think about the standard function. We're going to go explore real quick. We have f of x. Let me copy it. I'll copy it. Control copy. We're going to go to Desmos. We're going to go to calculator, graphing calculator. Put this over here. They have no idea what this is. So maybe if I raise it to the power, I don't know if they recognize x function notation. Does it? No, it doesn't. But if you put in y, notice this, that's function notation. That's saying this function in terms of x, not f times x. That's not what that means. It's just a notation. Kind of like if you don't know what the ampersand symbol means, this one reads, let me show you. If you don't know what that symbol means or where it came from, you don't know what to do with it. Ampersand, ampersand, ampersand. That's what we call it. Where did it come from? Why is it named that? How did it originate? What does it mean? Okay. And per se, and we need to change this to something. We could either just get rid of it altogether and then hit enter. What's going on here? Oh, do they not recognize that it's times? Okay, I don't know what happened there. So 4, maybe they do recognize f of x is equal to 2 times, nope, it was 4 times 2 to the x. Oh, they do recognize that notation. So what happened instead is when I copy pasted it from here, it had some sort of text that this system didn't recognize. But notice how this is identical. F of x is equal to 4 times 2 raised to the power of x, as is this. So just remember, using tools appropriately and strategically is a skill. Learn it. Don't give up on it. Reach out for help. Okay, there we go. There's our graph. What was our question? Which graph represents it? Okay. If x equals 0, 2 to the x, 2 to the 0, what is 2 raised to the power of 0? It's a rule of exponent. Never going away. 1,000,000. We'll just do 100 to the power of 0 is 1. Anything raised to the power of 0 equals 1. Okay? So when x equals 0, this whole thing will equal 1. So f of x, the graph, will equal 4. And that makes sense. That's our y-intercept. So then I'm going to copy this, control copy, control V. If I change this to -4, well, not only did it reflect it, it also made our intercept -4. What if I just changed it to 2? There we go. There's our green graph to 2. Okay? So just kind of use that to help you pay attention to what's happening to the graph. It's great practice with observation skills, cause and effect in math class. You get to practice your cause and effect, finding what happens when things change, and you can apply that general idea outside of algebraic equations. But here you can test it. You can test, oh, what does this do? Okay, we're looking for the graph to cross at 4. Cross at 4, cross at 1. But again, whatever you have here for your variation, 4, 5 to the x, look, that you might have to zoom in. That crosses at 5. That's not what we're looking for. This crosses at 4. That's good. Ooh, this crosses at 4 too, but look how it's going the wrong direction. This is decay, and whether or not you graph it, maybe you don't graph it, you could still see that that's not the right graph because this is greater than 1. So it's going to be a growth function. Okay. And then that crosses at 3. Okay, so this one, let's zoom in. We're going to look for it to cross at 5, and it's a greater than 1, so it's going to be a growth function intersecting the y-axis at 5. But again, you can graph it. Boop. Growth function. This is not it. It crosses at 5, but it's a decay function. So this value would have to be between 0 and 1. Question 2. Which graph represents 2 times 1/3 x? So let's just go graph it, right? Because we have this. We'll leave that up, but I'll turn it off. I'm going to change this. And what was it? 1/3? 1/3. 2 times. So 2 times 1/3 x. If we need these now. 2 times 1/3 x. Crosses at 2. Makes sense. That's that value right there. When x equals 0, 1/3 still equals 1. Okay, let's go see if we can find it. Okay, notice how this is the wrong direction. Oh, look, it crosses at 2. See what the other one's. Okay, this one crosses at 1 and it goes up. Notice how this is a growth function. This is a decay function, and that makes sense because right here is less than 1 and greater than 0. So we have a decay function. Okay, and again, this one is a reflection, and we talked about that today in class, like what happens, okay? Let's see if we can actually get that. We can get this one. Watch, we should be able to get this graph if I just put a negative symbol in front right here. If I just put a negative symbol here, boop, there we go. See, we get this graph over here. Pretty cool, huh? Okay, all right, let's keep going. So whichever one you have, whatever variation you have, you need to go ahead and graph it. Ooh, this is a fun one. The negative x. Let's graph it. No, I'm going to just, okay. So I'm going to get rid of this 2. I'm going to now add a negative symbol up by the exponent. So you need to be careful and make sure it's up by the exponent. Oh, it suddenly turned into growth. What? Decay, growth, decay, growth, decay, growth. How is that happening? What is going on here? Okay, so in class I talked about this. This is a case of understanding laws of exponents. This can be rewritten. Oh, okay, it confused me. We can rewrite that as x, 1 to the negative x, I confused myself, over 3 to the negative x. Okay, but rules of exponents, this is just 1. 1 to the power of any number will always be 1. You can check that. So this will be 1, but 3 raised to the negative x, this, I can flip it to make it a positive. So this will become back into the numerator and become 3 to the x. So using rules of exponents, I can see, aha, 1/3 to the negative x is the same as 3 to the x because of that negative exponent and the way it works. So hold on, let me clear screen, back, x, 3 raised to the power of x. They're the same. Green, purple. They're the same. Okay, just keep thinking about that. It's important. So there you go. We graph this for question variation 2. Just graph your graphs and try to match them. Think about why. Think about what's happening. The asymptote. All right, I'm going to graph this. 3x plus 6. Let me get rid of some of these. 3x plus 6. Let me change my graph. Aha. Okay, there is an asymptote at y equals 6. Okay, see that black line? That's the asymptote. If I zoomed in really close, it would get very close to that, but it won't ever touch. Okay, and I'll zoom out. Notice how it looks like it's a straight line, but over here, it's still slowly moving. There's no asymptote over here. It's actually going to be able, wow, look at that, to keep going. It looks like there's one. It looks like it'll never get past one. Look at that. That's crazy. Anyway, but the horizontal asymptote can be defined by this term in an exponential equation. So whenever you add or subtract, so if we subtracted this, it's going to drop down there. Watch, it's going to drop, boop, down to, it crosses at -5, and you can think, I wonder why. I wonder why. I really wonder why. Oh, because at 0, this is 1, and then 1 minus 6 is -5. Okay, anyway, but at that line, y equals -6, we have a horizontal asymptote. So this invisible line, that line's not really there, but if you zoom out, you'll see that purple never crosses that red line. So whatever yours is, you're looking right here to decide what the asymptote is at. Question 4. Question 4, what is the range? So here, we're also looking at what does the graph look like, and then where is the asymptote? So let's go ahead and graph it. -3, we're going to put a negative, and we're going to do -1. I'm going to get rid of this. I'm going to zoom back in. Ooh, so look how this is, it's going to keep going. Eventually, it's allowed to keep going. Nothing's stopping it. Maybe really far away, it's just going to keep slowly edging over. Maybe not. I don't know. I think about end behavior limits. We'll talk about that one day. But look at this. Look how it looks almost straight. And look at y equals -1. Okay, so now as I zoom out, not thinking about the domain, but thinking about the range, the y values this graph is going to take on. So are there any y values up here? 1, 2, 5, 6, 20, 15, right? Are there any y values up here? The range? No. Because of this horizontal asymptote, because of the way exponential graphs work and this number, we won't have any y values, in this case, above -1. So the range of this graph is y greater than, nope, I have that backwards, y less than -1. We don't even put or equal to. We don't even put or equal to. So let's go see if that's an option and the vocabulary they use. The set of real numbers less than -1. Y less than -1. This vocabulary is just exactly that. Y less than -1. Y can be any real number. It's implied that we're in the real numbers, but very good. Question 5. So again, if you have a different variation, graph it. Take a look at the graph. See which way y is going, right? This one was across down here, so it's going to go down. What about this variation? Okay, +4, but it's still facing this way. It's still reflected, so it's still going to probably be like up like this, up at 4. You have to look. Okay, so then 5. Look at your graph. Look where it can go. And if there's no positive y values, then it's all the values less than a certain number. The set of all real numbers less than a certain number or more than a certain number. Okay. What is the equation of the function shown in the graph given that the equation's parent function, the changes we talked about today, with the changes we explored with marble slides, 1/3 to the power of x. Well, look at the asymptote, -2. Boop. That's pretty good. Again, you could graph all of these, but hopefully that was helping you. We talked about that in class. So let's see this one. -3. Let's take a look at the last one. -4. There you go. All right, good job. Keep up the good thinking. Try to follow along, ask those great questions. And as always, I'm just an email or a phone call, or, well, Teams isn't working. Again, message away.